Most clothes today aren't made from one material. A single t-shirt might mix cotton, polyester, and a bit of elastane, all twisted together at the fiber level. That's why recycling them is hard. You're not just dealing with fabric, you're dealing with different polymers locked together, plus dyes and chemical finishes designed to never come out. Start with the chemistry. Cotton is mostly cellulose. That's a natural polymer made of glucose units linked together, held tight by hydrogen bonds. It doesn't melt, it burns, and it's very hard to dissolve. Polyester, usually PET, is a synthetic polymer held together by ester bonds. Those bonds can be broken with the right chemistry. Nylon has amide bonds, which are tougher. Elastane is even more complex, and small amounts can disrupt everything. Mechanical recycling just shreds clothes and spins the fibers again. Chemically, nothing changes. Blends stay blended, fibers get shorter, and quality drops. That's why blended fabrics push recyclers toward chemical methods. Mechanical recycling moves material. Chemical recycling changes molecules. Chemical recycling starts by asking one question. How do we separate these polymers? There are three main strategies. The first is selective dissolution. You use a solvent that dissolves one polymer but leaves the others solid. For example, certain solvents can dissolve cellulose by breaking its hydrogen bonding network. Polyester stays solid. You filter the polyester out, then add an anti-solvent so the dissolved cellulose precipitates back out and forms a new fiber. The key chemistry is solubility and hydrogen bonding, and the solvent has to be recovered or the process fails environmentally. The second strategy is depolymerization. Instead of dissolving a polymer, you cut it back into its building blocks. Polyester is the classic example. Its ester bonds can be cleaved by hydrolysis, glycolysis, or methanolysis. Long PET chains turn into small molecules like terephthalic acid and ethylene glycol. Small molecules are easy to purify by crystallization or distillation. Once they're clean, you polymerize them again and get polyester that behaves like virgin material. Nylon can be depolymerized too, but it needs different conditions because amide bonds are more resistant. The third strategy uses enzymes. Enzymes act like extremely selective chemical scissors. Cellulase enzymes cut cellulose into sugars. Engineered enzymes can break PET into its monomers at relatively low temperatures. The advantage is selectivity and lower energy. The drawback is speed, cost, and sensitivity to dyes and additives. In practice, these strategies are combined. Imagine a pair of stretch jeans made from cotton, polyester, and elastane. First, machines identify the fibers using infrared spectroscopy. Zippers and buttons come off, the fabric is shredded to increase surface area, dyes and finishes are partially removed with washing or solvent extraction because they can poison catalysts or discolor new fibers. Next, the polyester is chemically targeted. In one approach, glycolysis breaks polyester, and often elastane too, into soluble monomers while cotton stays solid. The liquid phase contains polyester building blocks. The solid phase is mostly cellulose. You separate them by filtration. Then, purification does the heavy lifting. Polyester monomers are crystallized, washed, and distilled until impurities are gone. Those monomers are repolymerized into new PET and spun into fiber. The cotton fraction can be dissolved and regenerated into a new cellulose fiber, or broken down further into sugars for other uses. Dyes matter because many are designed to bond strongly to fibers. Some are physically trapped inside polyester, others are covalently bonded to cellulose. Chemical recycling works because either the dye is extracted during dissolution or it's left behind when the polymer is broken into monomers and purified. That purification step is expensive, but it's what makes closed-loop recycling possible. The chemistry works. The limits are practical. Different garments contain different blends. Elastane causes problems out of proportion to its amount. Solvents must be recovered. Energy and cost matter. At its core, mixed fiber recycling is about reversing the chemistry that made modern clothes possible. Different polymers were locked together to make performance fabrics. Recycling unlocks them again, selectively, one bond at a time.